Hello, I am Desmond Edagese. Welcome to Maths class. Now, in our theme today, we have statistics, and we'll be looking at the topic probability. This is the second video in the series probability. It promises to be exciting. Let's go on into our class. Now, here are some of the things that we'll be looking at in our class today. We'll be looking at what theoretical probability is. Remember, in the first video, we looked at what experimental probability is. Well, in this class, we'll be looking at what theoretical probability is. We'll also learn what mutually exclusive events are. We'll learn about independent events, and then we'll see what dependent events are. And of course, we'll be carrying out calculations in all of these events. Now, what is theoretical probability? While we tried to describe experimental probability in our first class, we said it is based on actual experiments that are carried out. Theoretical probability, on the other hand, is the opposite of our experimental probability. Because in this case, we do not actually conduct an experiment. We don't have results from experiments with which we work. Theoretical probability is instead exact values that can be calculated by considering the physical nature of the given situations. So, for instance, you already know that a dice has 6 sides, and you know the number that is written on each side. So when you throw a dice, you can easily calculate which of those numbers may come up. It does not require an actual experiment. We instead make use of our knowledge about a particular situation. We make use of logical reasoning, and we make use of formulas, with the assistance of sample spaces to calculate the probability of an event happening. For instance, the probability of throwing a 5 on a fair 6-sided die is simply 1/6. We did not carry out an experiment, we're just surmising. Since every one of the 6 faces is equally likely, we know this information, so we can easily use it to calculate our theoretical probability. Now, P is mostly used to annotate, probability when we are carrying out calculations. So if P is the probability of an event happening, then P lies in the range 0 and 1. P less than 1 and P greater than 0. That range gives us the range of our probability. The probability of an event not happening is P prime. Is written as P prime. P prime is 1, which is the certainty that the probability is very certain to happen, minus P. Probability can be described also in set language. So we may say P of R, meaning the probability of a required event R happening, for instance. And of course, P of R is when we write out the formula that we already know, probability is required outcome all over all possible outcomes. We can write it in set notation as this. P of R, that is the probability of event R happening, is NR, which is the number of required events R, all over N sigma. Sigma, of course, is a symbol. We use it to represent every possible outcome. While R represents, it could be any letter, It could be any letter, take notes. R for here is representing our required outcome. Now, let's carry out some examples to understand theoretical probability better. Zainab throws a fair 6-sided die. What is the probability that she throws a 9, What is the probability that she throws a 4? What is the probability that she throws a number greater than 2? And what is the probability that she throws either 1, 2, 3, 4, 5, or 6? Let's take it one after the other. What is the probability that she throws a 9? From knowledge or from understanding the physical nature of a die or a dice, we know that a dice has 6 sides. And each of those sides is labeled 1, 2, 3, 4, 5, and 6. So a dice does not have 9 sides. The probability of throwing a 9 is therefore 0. Impossible. Remember our number line range. It ranges from 0 to 1. 0 is impossibility, and 1 is certainty that it will happen. So probability of throwing a 9 is 0. The probability of throwing a 4, on the other hand, is what? 1 all over 6. Why? Because there is just one chance in 6 of throwing a 4. 4 appears within our dice just one time. And of course, the total number of possible outcomes are 6. There are 6 sides. So we have 1 over 6 as the probability of throwing a 4. Now, what is the probability of throwing a number greater than 2? Let's list the numbers again on a dice. We have 1, 2, 3, 4, 5, and 6. Which of those numbers are greater than 2? 3, 4, 5, and 6 are greater than 2. So we have 3, 4, 5, and 6. How many are they? 1, 2, 3, 4. So the number of required outcomes are, there are 4 required outcomes. Total outcomes or total possible outcomes are 6. So we simply have 4 over 6. Which of course, if we further simplify, would have 2 over 3. So the possibility of throwing a number greater than 2 is 2 all over 3. Now let's take a look at the last one. What is the probability of throwing a number that is either 1, 2, 3, 4, 5, or 6? What is the number of our required outcomes? There are 6 required outcomes. 1, 2, 3, 4, 5, 6. 6 required outcomes. So we have 6 all over total possible outcomes, also 6. 6 divided by 6 gives us 1. So this is a case of certainty within the number line. Okay, we say 1 indicates that it is certainly going to happen. So if you throw a dice and you are asked, what is the probability of getting 1, 2, 3, 4, 5, or 6? You have listed all the possible outcomes. That probability is certainly 1. So you will certainly get one of these numbers that were required. So 1 is our answer. Now let's take another example. A letter is chosen at random from the alphabet. Remember, your alphabet has 26 letters in them. Find the probability that that letter is an X. Find the probability that the letter is V or X. Find the probability that one of the letters of the word square is selected. Square is S-Q-U-A-R-E. Also find the probability that not one of the letters of the word chair, C-H-A-I-R, is chosen. All right, so let's begin. Sigma represents our total number of possible outcomes. Okay, we have the set of letters A to Z, A, B, C, D, which basically there are 26 of them. Okay, so the number of possible outcomes is 26. Now, let A represent the set X that we've been asked to find the probability of it being chosen. Then, probability of A, therefore, is number of our chosen or selected letters, there's just one, X, all over the number of possible letters within the alphabet, 26 of them. So, we simply have 1 over 26 as our answer. Probability of getting a V or an X, okay, that means we are picking 2 items. Okay, so we simply have number of required outcomes. There are 2 required outcomes, V and X. So we have 2. Number of possible outcomes, 26. 2 over 26 gives us 1 over 3. Next, find the probability of getting one of the letters of the word square. Square is S-Q-U-A-R-E. E. Okay, so let's see the set of numbers SQUARE. The number of letters within the word square, there are 6 of them. So you have 6. All over the number of letters within the range of the alphabet, 26 of them. So we have 6 over 26. And this simplified gives us 3 over 13. Finally, we've been asked to find the probability that it is not one of the letters chair. Chair has how many letters? 1, 2, 3, 4, 5. Okay? Remember they said not one of them. So if you take 5 letters out of the total number of alphabets, we have 26 minus 5. That gives us 21. All right? So what we're actually being asked is to find the probability of getting 21 letters out of our total outcome. So it's simply 21 over 26. But another way we can write it out mathematically, okay, is to say 1, which is the certainty of getting 26 over 26, minus the probability of getting either of the letters in our word chair, CHAIR. It therefore means that first we'll find the probability of getting the letters within the word chair. There are 5 letters. That's our number of required outcomes, while the number of possible outcomes is 26. So 5 over 26 is the probability of getting a letter from this word picked from the total number of alphabets. To get the probability of picking not one of these letters, that would be 1 minus the probability of getting one of the letters. The probability of getting one of the letters to be 5 over 26. So 1 minus 5 over 26 also gives us 21 over 26. So it's the same thing that we came about earlier. Now, in probability, there's something called mutually exclusive events. Remember, we learned what an event is in our first class before now, okay? We said an event is one of the results of our experiment, okay? So a mutually exclusive event, it's a term that describes 2 or more events that cannot occur together at the same time. That is, they cannot occur simultaneously. For instance, it is impossible to toss a single coin and get the result of a head or a tail at the same time. Now imagine it, you toss a coin, okay? That is a fair coin, not a coin that has 2 heads or 2 tails. One that has a head and a tail. So it's either the head shows up or the tail shows up. You cannot have the 2 showing up at the same time. When you have such a case, you say, okay, the event of getting a head and getting a tail, they are mutually exclusive. They cannot occur simultaneously. They can occur one after the other, but not at the same time. So in such case, the event follows what we call the addition rule. That is, the separate probabilities, they are added to give a combined probability. This is an example of what we're trying to explain. So if you have 2 events, V and L, for instance, they are exclusive one of another, okay? They do not interlap. They do not interlap. Now, the addition rule states that the probability of V is added to the probability of L. So we have probability of V union L. Take note that the addition law, all right, is used to solve problems that contain words like or words that contain either and or within the same sentence, or also words that contain maybe just either. In either of these cases, okay, we make use of what we call what? The addition law. Now let's take typical examples. Example 1, a number is selected randomly from the set 3, 6, 9, and so on, up to 30. Okay? So we've been asked to find the probability that it is either a factor of 27 or a multiple of 6. The number selected, what is the probability that it is either a factor of 27 or a multiple of 6? Let's go on. Sigma represents the total number of outcomes. So we have within the set 3, 6, 9 up to 30. So you have 3, 6, 9, 12, 15, okay, 18, 21, 24, 27, and 30. There are 10 numbers in that range. Now let F be the factors of 27. And it is a set of factors of 27 within the range 3 to 30. The factors of 27 there are 3, 9, and 27. Let M represent the multiples of 6 within the range 3 to 30. So you have multiples of 6 as 12, 18, 24, and 30. So we see that F and M, they are what? They are mutually exclusive. And remember the clue we just gave us. We said when you have words like either in your question, you make use of what? The addition law. And of course, the addition law states that we add up the different possibilities to get a combined probability. The different probabilities, are added to get a combined probability. So let's get our different probabilities. What is the probability of getting F? F, remember, is the factors of 27. Okay? So the number of F, there are how many? 1, 2, 3. We have 3 numbers there that are factors of 27 within our range. So we have 3, required outcome 3. All over, what are the possible outcomes? There are 10 possible outcomes. We listed them as 3, 6, 9, 12, 15, 18, 21, 24, 27, and 30. There are 10 of them. So 10 is the total number of our possible outcomes. As the sample space, there are 10. 3 over 10, therefore, is the probability of getting an F. Probability of getting an M, that is the multiples of 6. How many numbers do we have? 1, 2, 3, and 4. There are 4 numbers, that is required outcomes, 4. While the number of our total possible outcomes, of course, we said is 10. So 4 over 10 simplifies to give us 2 over 5. The probability that either F or M happens, okay, either or, okay, we make use of the addition rule. So we add up our probabilities, 3 over 10 plus 2 over 5. And that gives us 7 over 10. So 7 over 10 is the probability that it is either a factor of 27 or a number that is a multiple of 6. Let's try another example. A bag contains 3 red balls, 4 blue balls, 5 white balls, and 6 black balls. A ball is picked at random. What is the probability that that ball is either red or blue? So again, we see the magic word, or. It means that we will make use of the addition rule. Let's go ahead with our question. Sigma represents, okay, the total possible outcomes. 3 red balls, 4 blue balls, 5 white balls, 6 black balls. The set of number of balls within there, okay? So we have 3 plus 4, 7, and 5, 12, and 6, 18. There are 18 balls, okay, within the bag. Let R represent the red balls. So the set of numbers of red balls within our bag is 3. Okay? We have 3 red balls. Let B represent the blue balls. The set of the number of balls that are blue within the bag was given to us as 4. So we have 4 red balls. We've been asked to find out the probability that the ball that is picked is either red or blue. Okay? So we make use of our addition rule. But first, we find the separate probabilities of our red ball and our blue ball. Probability of our red ball is the number of red balls within the bag, 3. That's the required outcomes. Total number of balls, we said, is 18. So 3 over 18, simplified, is 1 over 6. Probability of getting a blue ball is the number of blue balls within the bag. 4 is the required outcome. Total possible outcome is 18. 4 over 18 is simplified to give us 2 over 9. The probability that either a red or a blue ball is picked is therefore making use of our addition rule. We add up the separate possibilities or separate probabilities. 1 over 6 plus 2 over 9. That gives us 7 over 18 as our answer. Next, we'll learn about the independent events. Independent events. In probability, when you have two events, A and B, they are said to be independent if the fact that A occurs does not affect the probability of B occurring. It doesn't stop B from taking place. An example is tossing a coin and getting a head as a result. At the same time, rolling a dice, you get 5 from a 6-sided die. There is no interrelation, okay? Each event is independent of the other. The first event of, okay, tossing that coin and the event of rolling that dice, they don't affect each other. In such a case, what do? We follow the product law. Now, the product law simply multiplies the individual probabilities of each instance. That is, the separate probabilities are multiplied to give us what? A combined probability. Now, take note that the product law is used to solve problems when they contain words like and or both / and. That is, when both and are in the same sentence, or just and is within the sentence. Let's take some typical situations. Example 1, a die is thrown and a coin is tossed. Two separate events done at the same time. What is the probability of getting both a 6 and a tail? What is the probability? So we have our magic word, and. It means that we use what? The product rule. Now, what do? There are two ways to go about it. We can simply set up a sample space. Remember what we said a sample space is? The total number of possible outcomes. Get a paper, write every possible outcome. Okay? And then it's simplified for us to answer our question. Write out all the possible events. Okay? So let's set up our sample space like this. Write out every possible outcome in our events. So we have our dice and we have the coin. The dice has 6 sides, so there are basically 6 possible outcomes. So let's assume that we are rolling the dice 6 times. That will limit the number of times we also throw our coin if we are to do it simultaneously. So the first throw of our dice could give us 1. The next one, 2, 3, 4, 5, or 6. 6 possible outcomes. For the coin, we have the head and the tail. The possible outcomes of the head could follow for each toss or each throw of our dice. When 1 is thrown, we could also toss our coin to get a head. When 2 is thrown, we could also toss our coin to get head again. When 3 is thrown, 4 is thrown, we keep getting the head. So these are all possibilities. Dice 1, head 1. Dice 2, head 2. These are all possibilities. Also, you could also have another possibility of a tail. When 1 is thrown, we could toss our coin to get a tail. When 2 is thrown, toss our coin to get a tail. Each instance getting a tail for each toss of the coin. So these are all possibilities. But the possibility that is required is what? 6 and tail. So we've listed out all the possible events. Okay? So it's either 1 and a head or 1 and a tail, either 2 and a head or 2 and a tail, and all of that. There are in total 12 possible events. So which of this gives us our required outcome. It is this here where they interlap. We have, okay, the toss of our die to give us 6, and we have tail to give us 1. So we find that we have 1. For the possibility of getting a 6 is 1 over 6, and the possibility of getting a tail is 1 all over 2. So basically, we find that out of the 12 possibilities, 6 here and 6 of the tail, we have together 6 and 6, 12. So it's just 1 possibility of getting 1 6 in our dice and 1 tail is 1 over 12 out of 12 possibilities. This is making use of the sample space, but we can simply make use of a formula to get a faster result. If PS represents possibility of getting a 6, PS is what required outcome all over possible outcome. Required outcome is 1. There's only 1 possibility of getting 1 6 out of the roll of your die. So we have 1 over 6. If PT represents the possibility of getting a tail, okay, we have just 2 possible outcomes. Tail is just one side, so it's 1 over 2. From our product rule, we said multiply both separate probabilities to get a combined probability. So we simply say PS times PT, P of S times P of T, probability of S times probability of T, gives us 1 over 6 times 1 over 2, and that's 1 over 12. So it's the same thing we get from mapping out our sample space and manually locating our answer. Let's take another example. A card is chosen from a pack of playing cards, and then it is returned to the pack. A second card is now chosen. So we see this is an independent event. First event, card was chosen, and it was returned. If it was not returned, the number of cards would have reduced, and it will affect the calculation of the second event. But since it was returned, it's an independent event. So the first event does not affect our second event. Okay, what is the probability that both cards are black? Remember, in our first class, we said try to get familiar with the pack of cards. There are some properties the pack of cards have. Remember, we said we have a total of 52 cards. We said we have 4 suits within the cards. We said we have spades. We have club. We have the diamonds. These are all suits. And then we have the hearts. We said there are 13 each. Okay? These are some of the properties. And then we said that each card has an ace, a jack of cards, a king, a queen, and then you have numbers ranging from 2 to 10. One other property is that clubs and spades, they are colored black. Okay? While the diamonds and hearts are colored red. So these are all things you need to know. When you are asked questions on probability that has to do with a card, some of this knowledge will help you. So now that you've been asked, what is the probability that both cards are black? So now we know that there are 13 club cards and 13 spades cards, which are black within the pack of cards of 52. So therefore, when we pick the first time, the probability that we are picking a black card will be what? 26. Remember, there are 13 black club cards and 13 spade cards. So 13 and 13 is 26. There are a total of 26 black cards within the pack. That's our required outcome. Total outcome is 52. That is the total number of cards within the pack. 26 over 52 simplified is 1 over 2. Okay? The cards were replaced, and then we picked a second time. What is the probability that a black card is picked again? Same probability. We have 26 black cards all over a total of 52. Again, we simplify to get 1 over 2. Now, by the product rule, remember we said when you have words like both, you make use of what? The product rule. Therefore, the product rule simply says we multiply each individual probability to get a combined probability. The combined probability that both cards are black are what? 1 over 2 times 1 over 2. That gives us 1 over 4. So the probability that both cards are black is what? 1 all over 4. Now we go on to learn about dependent events. Dependent events. We've already learned what independent events are. Independent events, that is, the prior or the previous event does not affect the next event. Well, in dependent events, it's the opposite. A previous event affects the subsequent event. When we have such a situation, we call that a dependent event. For example, when you pick a card from a pack, okay, or you pick marbles from a bag, and you do not replace them, they are not replaced, before you pick another one, that is another event, what happens? The initial total number, that is the probable total outcome in the first event, is reduced by 1. So you have a calculation that is different because the total outcome will no longer be the same. Okay, so it will affect the total outcome when that probability is calculated. When you have such a case that a card or a marble or whatever is done without a replacement, you have a dependent event. That's just an example. The number remaining in the second peak of the sample space is reduced. That's what we explained. We therefore say it's a dependent event. So, let's take a typical example. 4 girls, 5 boys. They all put their names in a box. They wrote it on a piece of paper, put them in a box. And then a name is picked out at random from that box. Picked out without replacement. That is, without replacing the first name that was picked, another name was again picked at random. What is the probability that both, that's our magic word, both names that were picked the 2 times are both the names of girls? What is the probability? Let's break it down. First pick. Remember, there are 4 girls and there are 9 names. 4 girls and 5 boys. Together, 9 names. 4 girls, 9 names. The probability that a girl's name is picked is what? Required outcome, girls. 4 girls, 4. All over, total number of names, 4 and 5. 4 boys, 5 girls gives us 9. 9 names. So 4 over 9 is the first probability. Now we did another pick. Remember, we did not replace the first initial name that was picked. After picking a name, what happens? And we pick the name of a girl. The girls have reduced. So we have 3 names of girls. And total, we have 8 names, no longer 9 names. So the probability that a girl's name is picked this time around is what? 3, which is our required outcome all over 8. So our total outcome from 9 has become 8. 3 all over 8 is the second probability. Now, since we've seen the word both, we have a clue that the product rule will be applied here. The product rule simply states that we multiply, okay, our individual probabilities to give us a combined probability. So combined probability that both names are girls becomes what? 4 over 9 times 3 over 8. This is us 12 over 72. When we simplify further, we get 1 over 6 as our answer. Let's take a look at another example. 5 cards are lettered A, B, C, D, E. 3 of the cards are chosen at random, one after the other, without replacement. So without replacement, we immediately know that these are dependent events. Without replacement, and then they are placed in the order shown. This is the order shown. So we have first card, second, third. Order. What is the probability that the cards spell the word bed? What is the probability that a B will come in here, an E will be picked next, and then a D will be picked next? Let's take a look. First, we'll do probability for B. Bed spells B-E-D. what is the probability that B first will be picked? First pick, there is one other, okay, and there are 5 cards. At the very first instance, we have 5 cards, A, B, C, D, E. So what's the probability that B will be picked? Required outcome is B. We have just one B, so we have 1 as required outcome. Total possible outcomes, we have 5 cards, so we have 5. Therefore, probability of a B is 1 over 5. Second pick, remember, as B is picked, it is not replaced. Okay? It therefore means that instead of 5 cards now, we have 4 cards. And the B is gone. Okay? So we have, for the second pick, one other, and there are 4 cards, no longer 5 cards. The probability that E is picked from the 4 cards is what? 1 all over 4 possible cards, 1 over 4. Again, as E is picked, it is not replaced. So we have, instead of 4 now, we have 3 cards left. Out of the 3 cards, we do a third pick, trying to see what is the probability that a D will be picked from that card. Okay, probability of picking a D is 1. D is just 1. And we have 3 cards left, 1 over 3. So we have probability 1 over 5, 1 over 4, and 1 over 3. Now, we've been asked what is the probability that the cards spell the word B, E, D. Remember, in this case, we make use of a combined probability. Combined probability. So we simply say multiply each of the individual probabilities to give us what? That combined probability. 1 over 5 times 1 over 4 times 1 over 3. That gives us 1 over 60. Okay, so we have 1 over 60 as our combined probability. Now, to summarize, we'll take a look at all that we've learned for today. We learned about theoretical probability. We said it does not involve any actual experiment. So it's the opposite of experimental probability that we learned in the first class. Instead, it involves the use of logical reasoning to create sample spaces and formulas to calculate the probability of our event ever happening. We also learned what mutually exclusive events are. It describes situations where 2 or more events cannot happen simultaneously. We also learned that 2 events A and B are called independent events when event A does not affect the probability of event B from happening. And finally, we learned that when an event B is affected by a previous event A, we say that event is a dependent event. Now, before we go, we'll do 2 quick questions to try to remember all that we've learned. Now, let's look at question 1. A card is chosen at random from a pack of playing cards. What is the probability that it is either a hat or the queen of spades? So we need to have knowledge of what constitutes a typical pack of cards. Let's refresh our minds again. We said there are 52 cards within the pack. We said we have 4 suits. Remember, we said we have spades. 13 of them, 13 spades. We have 13 clubs. We have 13 hearts. And we have 13 diamonds. So all of that gives us 52. Now, we said that in each of these suits, there is an ace, a jack, a king, a queen, and numbers 2 up to 10. All right? So let's look at our question again. What is the probability that it is either a hat, okay, or the queen of spades? Now, a hat. Hat is just one of the suits, and we said there are 13 of them. So it simply means that our required outcome is 13. All over the total number of cards, which is 52. So we have the probability of getting a heart is 13 over 52. All right? While the probability of getting the queen of spades, okay, so we have 13 spades, and we have just one queen within our spade. So we can have just one possible queen of spades within the whole card. So the possibility of getting a queen of spade is just one all over the total 52 cards. Therefore, using our addition rule, where we have our magic word or, we simply add up the separate possibilities to get a combined probability. So we have probability of union H and Q. So you have 13 over 52 plus 1 over 52. This gives us 14 over 52. Simplifying, 2 here, 7, 2 here, 26. We have 7 over 26 as our answer. Let's see which of the options gives us the correct answer. Is it A, B, C, or D? Option C gives us our answer, 7 over 26. Let's take our last question for this class. In a game of chance, an arrow spins at random. Okay? So here's our game. This arrow here is spun round and round and round. Okay? When it stops, it points to one of the 8 sectors numbered as shown. So we have numbers 1, 3, 1, 3, 1, 2, 4, and 2. Find the probability that the arrow will point at 3 or 4. What is the probability that it will end at 3 or 4? Okay? Again, we have the word or. So we have an idea where we are going. So let's find the probability of getting a 3 first. What is the probability of getting a 3? There are 2 3s out of a total of 1, 2, 3, 4, 5, 6, 7, 8. So we say probability of getting a 3 is what? 2 possible 3s all over 8 total 3. So 8 over 2 is what? 1 over 4. Probability of getting a 3 is 1 over 4. Probability of getting a 4 is what? How many 4s are there? Just 1. All over total possible 8. So the probability of finding, or the probability of it spinning to point at a 3 or a 4 is the addition of our separate probabilities, okay, using the addition rule. So we say 3 union 4, which gives us 1 over 4 plus 1 all over 8. And of course, this gives us 8. This gives us 2 and 1. This gives us 3 all over 8. Let's take a look at our options. Is it A, B, C, or D? Option B gives us the correct answer. And with that, we've come to the end of our very interesting class for today. I'm sure you had a nice time. We'll have a 3rd series in this video, and I definitely look forward to seeing you in that video. Once again, I'm Desmond, and I hope to see you soon. Bye for now.